So, welcome back. So, can you, one of you, please say or type, like, am I audible? Okay. So, okay, thank you. Thank you so much. Yeah, just saw the message. Okay. So, welcome back to the week 2 of the problem solving session for the course Thermodynamics taken by Professor Anand from IIT Palakkad. And in this week, we will be dealing with uh, work interactions, which is, as we discussed in the previous session, that heat and work interactions are the fundamental modes of energy interaction for any thermodynamic system. So we'll be discussing that. We'll be also be dealing with the different types of work interactions, and we will be primarily focusing on, or we will be focusing on in detail about the PdV work. So we'll see how the different, how the expression for the PdV work changes for different uh, types of processes: isothermal, adiabatic, isochoric, isobaric processes. So we'll see how the expression for the PdV work changes accordingly, and then after that we'll be solving some numerical problems, and also some conceptual problems, and so that so that it could help us to, or help each and every one of you to solve the uh, assignment problems for this week. Okay, so that's today's agenda. So I guess we can start. Okay, and again, as per similar to the similar to previous week, I will not be going deep through each and every definitions in the lecture slide. It was properly discussed by Professor Anand, so I will not repeat it again and again. But again, I will try to go through the concepts briefly. If you have any doubt, you can ask, or else our primary focus will be on solving the numerical problems related to this week's topic. Okay. Okay. So, work, as we know, in the purview of mechanics, can be defined as integral of f dot ds, and power is basically work done per unit time, or the rate of doing work. Okay. In the field of thermodynamics, work done can be considered, as I already mentioned, can be considered as one of the modes of energy interaction between the system and the surrounding. Okay. In terms of thermodynamics, or in the field, or in the subject of thermodynamics, work interactions or work done has a very standard definition. Okay, so sorry, so the definition goes like this: like, work is said to be done by a system during a given operation if the sole effect of work external to a system could be reduced to the raising of a weight through a distance. Okay, so I would like you to go through this definition once again. Like, of course, work done, as already you might have already discussed in class 11 and class 12. You already discussed what work done means, and it's basically the same. But in the context of thermodynamics, it has a very standard definition, and this definition is tend to be used by most of the textbooks and professors, and uh, all the standard what mode of understanding in thermodynamics. So this is a standard definition that they usually use. So I would like you to go through this definition once. So by this statement, it is basically trying to say is that it's not necessary that the work done should always have an have an effect of raising of a weight through a distance. It's not necessary. It is just trying to imply that any kind of work interaction that may occur in thermodynamic system can be reduced to that each effect can be reduced to a similar work done, that, similar amount of work done that is being uh, done while raising a weight through a particular distance. Okay, so it's just an analogy. So any kind of work interaction can be reduced to this to have a similar effect as the raising of a weight through a particular distance. Okay. So I hope it was clear. The definition should not be misleading. It's just a standard way of defining work done in the concept of in the subject of thermodynamics. Okay, this is just a standard way of defining work interactions. Okay, or work done. Okay, so now we will be discussing a very important topic, that is the sign convention of work done. Okay, so most of the standard thermodynamics textbooks or research papers that are dealing with the concept of thermodynamics follow this sign convention. That is, the work done by the system is taken to be positive, and the work done sorry and the work done on the system is taken to be negative. Okay, and similarly you will also see that when we discuss heat interactions, we will see that the work done on the heat transfer into the system is taken to be positive, and heat transfer out of the system is taken to be negative. Okay, this sign convention will be followed throughout the course of the throughout this course, and of course through any kind of subject that deal with the concept of thermodynamics. So this kind of sign convention is usually used. So most of the standard textbooks follow this sign convention, but there might be some authors or uh, uh, researchers that may use the opposite one. That's also correct. It's just their way of assigning a particular sign to the heat and work interactions. But this is the most standard way, and I will request or I will suggest you to follow the similar convention like this, because this would become quite handy if you are aware with the standard convention sign convention that is usually used. Okay, so once again, the work done by the system is taken to be positive, and the work done on the system is taken to be negative. Okay, so the work done by a system to upon the surrounding or other system that it is interacting with would be taken to be positive for the particular system that we are concerned with. Okay, similarly, the work done on the system is taken to be negative, and the work is done on the system by the surrounding or the different systems that it is interacting with. Okay, so it is not always necessary that the surrounding only does work on the system, or the system only works on the surrounding. It may also happen that there may be different number of several number of systems that are interacting with each other. So in that case, if you are focusing on a particular system, then the work done on the system by the other systems that we are not focusing upon right now can be taken to be negative, and the work done by the system on the other systems that we are not focusing upon can be taken to be positive. Okay, so I hope the sign convention was clear. Okay, so it's a very trivial thing to remember or understand, but it's very important as well. That's why I'm emphasizing upon it. Okay, so the first type of work interaction, or the first type of work interaction that we'll be discussing in today's session, is the displacement work. Okay, so this is defined as the mode of work involved. This mode of work is involved when a system boundary sweeps a volume interacting with its surrounding. Okay, and the volume swept may be against the surrounding or against the system itself, depending upon whether the system does work or not. So if you so defining it more clearly, like if the volume is okay, good evening. Okay, so if the volume is expanding against the surrounding, then the work is done by the system. Similarly, if the volume is expanding against the system itself, then the work is said to be done on the system. Okay, and again, this work can be evaluated only for a quasi-static process. Okay, again the term quasi-static comes in the picture. We will again see this definition again and again, so it's again very crucial to remember. Okay, so again, this diagram or the derivation was again done by Professor Anand, so I will not go in detail. I will just go through it briefly. If you have any doubt, you can ask, that's fine, but I will not I will not focus much upon the derivations deeply. Okay, so for understanding displacement work, Professor Anand used an example of a piston cylinder mechanism. So he mentioned that there is a piston at a particular location in the cylinder, which has, and the volume enclosed by the piston has a particular pressure that is given by P1. Okay, now if the piston moves very slowly to a distance of dx, so delta x, and again the term very slowly. Why very slowly? Because we are trying to achieve a process that is quasi-static or nearly static, nearly stationary. Okay, and this kind of processes are we are interested upon because such kind of processes are very close to reversible processes. Okay, and only those kind of processes which are quasi-static or reversible can be plotted in the PdV diagram, and their thermodynamic analysis can be done through our mathematical derivations, right? That's why we are saying that the piston is moving very slowly so that a quasi-static state can be obtained. Okay, say after expanding it reaches a pressure P2, then the pressure acting upon the surface of this piston, it can be given by force per unit area. Okay, now we know that work done delta W can be given as F into delta X. Okay, again delta W can also be written as P into A into delta X using this expression. Now A into delta X can be again written as delta V, but we know that since volume is a property of the system, we can write delta V as dV or an exact differential. Okay, so delta W can be written as PdV. Now if we want to evaluate the net work done from say process from point 1 to 2, then the work done from point 1 to 2 can be denoted as these two manner. Either we can use this notation or this notation. Like personally I like to use this notation, but again it's up to the choice of the individual. It's completely fine, but you can use either of them as a standard notation to denote work interactions from a particular point 1 to point 1 to point 2. So work interaction from point 1 to point 2 can be written as an integral of PdV from volume V1 to V2. Okay, or otherwise you can also write from point 1 to point 2. That's completely fine. This is the standard way of denoting the displacement work. Okay, see, it's not the net work but the displacement work. Okay, since we're only discussing the displacement work, because there can also be different types of work interactions, right, which we'll eventually see. But for displacement work, it can be denoted as integral of from point V1 to V2 of integral of PdV from point V1 to V2. Okay. So I hope it was clear. Again, just write your doubts in the chat box, or you can ask. It's completely fine. I'll just see if there's okay. Okay. So again, this integral can again be denoted through a PdV plot. So if we consider a graph whose x-axis denotes the volume or the specific volume depending upon the choice of the depending upon the problem. So and the y-axis denotes the pressure. Okay, so if we consider a particular process, say from point 1 to point 2, so this line, let me distinguish it using an arrow. So, yes, from point 1 to point 2, then the net work done from point 1 to point 2, or the net PdV work or the displacement work done from point 1 to point 2 is actually the area under this curve. Okay, there is total area, sorry, there is a total area under this curve denotes the net work done from point 1 to point 2. Okay, now the small elemental volume can be represented by a small strip of area within this curve. This is denoted as dV. So the net integral of PdV, it will denote the area under this curve and will thus give the net work interaction from point 1 to point 2. Okay, again this V can be either volume or specific volume depending upon the problem. Okay, if you are dealing with specific volumes in the problem, then this V means specific volume. If it is mentioning total volume or volume V, then it's the total volume. Okay, not the specific volume, depending upon the choice of the problem. So as we also we discussed this in the last week's session, that work done is a path function. I also emphasized why, because the work depends on the path that is being followed to achieve the to complete the process from point 1 to point 2 or point 2 to point 8. That's completely fine, but it depends on the path that is being followed to achieve that process. Okay, so Professor Anand again used a very good example to clearly show why is it so. So if there is two distinct state points, point 1 and point 2, and to complete the process from point 1 to point 2, if there are different parts, say A, B and C, like uh, the first process that is being used to achieve a process from point 1 to point 2 is from part A. Then and if the second process is through part B and the third process is from part C, you can clearly see that the area under the PDB curve changes when the parts used to achieve the process is changing, right? So it distinctly shows us why work as a path function, because since the area under the integral of the PDB changes with the path that is being followed to complete the process, that's why work is definitely a path function. And you will also see that how heat interaction is also a path function. There we will be dealing with the TS curve, or the temperature entropy plots. So there we will see how the area under temperature entropy plots gives the net heat interaction. Okay. Again, Professor Anand and also me also want to emphasize again and again that why the integration of the PDB curve can only be performed when the process is a quasi-static process. Okay. Why? Because it is only then that we can represent the process through a solid curve and then evaluate the integral. Otherwise, if the process is irreversible, then we cannot represent it on the PDB curve from a solid line, so the integration cannot be achieved. Okay. So now we will be dealing with the evaluation of PDB work for different types of processes. Okay. Sorry for that. So these lines of different colors show different types of processes. Okay. So the green curve shows the line for the constant pressure or isobaric process. Okay. So if we consider a standard equation or relation between pressure and volume, say PVN is equal to constant, then for n equal to 0 we will have this term equal to 1, then pressure becomes constant. Okay, so for n equal to 0 we have a isobaric process or constant pressure process. Okay. Similarly, if we have n equal to 1, I said n equal to 0, okay, for isobaric process. If I am mistaken, just trying to recall. Okay. So for n equal to 1, we have an isothermal process. So for n equal to 1, this equation will become this equation will become PV equal to C. Okay, or for different state points, we can write P1 V1 equal to P2 V2 equal to P3 V3 equal to some constant. Okay. Similarly, for n equal to gamma, we will have an adiabatic process. Okay, PV gamma equal to constant, we will have an adiabatic process. So an adiabatic process is a type of process which do not have any kind of heat interaction. Okay, we will discuss it when we are dealing with heat interactions. So the importance of adiabatic process or the distinction of adiabatic process will come into picture. Okay. Now, if n varies from any other values from other than 1, n or 0, then we define it as a polytropic process. Okay. We do not have a distinct value or specific value for n, then we define those kind of processes as polytropic process. Okay. Now for n equal to plus or minus infinity, it will basically imply that this term is comparatively very, very large or very, very small compared to p. So the existence of p in this equation becomes negligible. So we can write volume equal to constant. So these kind of processes are known as isochoric processes or constant volume processes. Okay. So now, after knowing these different types of PDB processes, now we will see how we can derive the expression for the work interaction for this PDB displacement work. Okay, or PDB work. Okay, PDB work or displacement work can be used interchangeably, so I am just using that. Okay. Now for isobaric process, that is a constant pressure process, the work done from point 1 to 2 can be evaluated using this equation, a standard equation for a displacement work, okay, or PDB work. Okay, so this is a standard expression. So any kind of just 1 minute. Sorry. So any kind of modification to this equation would come when we are defining the particular process through which this PdV work is achieved. Okay, this expression is a standard expression for the PdV work. Okay, so this is a fundamental expression. So any kind of modification to this equation or special form of this equation will come into picture when we are defining the process that we are using to achieve that particular displacement work or PdV work. Okay, so in the case of an isobaric process or constant pressure process, we will have P equal to constant, right? So the P will can come out of the integral. So we will have W1 to 2 work done from 1 to 2 as P into integral of dV from 1 to 2. So once we evaluate this integral, we will get the work done from 1 to 2 as P into V2 minus V1. Okay, for an isobaric process or constant pressure process. Okay, similarly for an isochoric process, just 1 minute. For an isochoric process, since volume is constant, the value of dV will be equal to 0, right? That's why the work done from 1 to 2 for an isochoric process is 0. Okay, now there's a very important catch. So one general question to all of you. Okay, just listen to the question very carefully. So is work interaction in a thermodynamic system 0 for is the work interaction in a thermodynamic system always 0 for an isochoric process? Listen to the terminologies. Is the work interaction 0 for a thermodynamic system for an isochoric process? Is it always 0? Can someone of you please say yes, no, and give the yes? Okay, one answer is yes. Yes. See, I think I might have misread the question, or you might not have listened the question to it very carefully. So I'm saying that, let me just write it. Okay, it's a very interesting term. So is work interaction, okay, work interaction equal to 0 for a oh sorry, is work, no, doesn't matter, interaction, I'm just equal is work interaction always 0 for a for an isochoric process? So let me see the replies. Yes, 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 open system. So see, if the system is open and if the control volume is changing, then we will not achieve a isochoric process, right? So it will not be isochoric process, right? If the system boundary is changing with the changing with time, then we will not achieve an isochoric process, right? So usually you need to have a isochoric process is achieved in a closed system where the volume remains constant and the pressure or other properties may change. Okay, it's usually achieved through that. Okay, so the answer is actually no. Like, see, I have used the terminology work interaction, and as I already mentioned that work interactions can be of different form. There are also work interactions which do not involve PdV work. Okay, there can be shaft work, electrical work done, right? So in that case, even if the volume is constant, the other kind of work interactions will come into picture and will give work done. Yes, will give work done is not equal to 0. Okay, so it does not necessarily mean that when volume is equal to constant, we will have 0 work done. Okay, so only the displacement work or the PdV work is 0. Okay, is that clear? Yes, thank you so much. Okay, so similarly, now we look into other type of process, that is an isothermal process. Okay, for an isothermal process we will have PV equal to constant. Okay, now if we substitute the expression for P as C by V in this equation, then we will get work done from 1 to 2 as integration of C dV by V from point 1 to 2. Okay, and if we evaluate this integral, we will get work done from 1 to 2 as c into the natural log of v2 by v1. Okay, now since we know that, let me just write it, pv equal to c would imply p1 v1 equal to p2 v2 equal to some constant. Then we can also write work done from 1 to 2 as p1 v1, it is basically c, into natural log of v2 by v1, or p2 v2, which is also equal to c multiplied by natural log of v2 by v1. Okay, so this is the expression for work done for an isothermal process. Okay, now for a polytropic process, we will have work done from 1 to 2 as integral of pdv from point 1 to point 2. Okay, now p can again be written as c into v to the power minus n. Okay, then work done from 1 to 2 can be written as integral of c v to the power minus n dv from 1 to 2. Okay, then work done from 1 to 2 will be equal to, then c can come out since c is a constant, then c times the integral of v to the power minus n dv, from point 1 to point 2. Okay, now if we evaluate this integral, we'll get that work done from 1 to 2 as c times v2 1 to the power minus n minus v1 1 to the power minus n divided by 1 minus n. Okay, now if we substitute the expression, the value of c first as, let me just show it, for v2 we can substitute c as p2 v2 to the power n. For v1 we can substitute c as p1 v1 to the power n, because p1 v1 to the power n equal to p2 v2 to the power n equal to constant. Okay, this is just a mathematical modification done to simplify the equation even further. Then after we substitute these values in the equation, we will get that work done from 1 to 2 is equal to p2 v2 minus p1 v1 divided by 1 minus n. If we multiply by negative sign with both the numerator and the denominator, we will get work done from 1 to 2 as p1 v1 minus p2 v2 divided by n minus 1. Okay, this is for a polytropic process. Now simply, if you substitute the value of n equal to gamma, because we know that pv equal to gamma is a constant for an adiabatic process, then if we substitute the value of n is equal to gamma, we will get that work done from 1 to 2 is p1 v1 minus p2 v2 divided by gamma minus 1. Okay, so is it clear up till this point? Okay. Example, see, okay, just 1 minute. See, so an adiabatic process, okay, polytropic process, examples for both of them. Okay, so let me just go back to the diagram again. Okay, so see, this value of n, the index in the expression for pvn equal to constant, this value of n is determined after various experiments that has been done while analyzing thermodynamic systems. Okay, so after doing various kind of, or say if one of the researcher is conducting and trying to achieve an isothermal state, this is again very difficult, but if he is able to achieve a isothermal condition while say doing a pdv work from point 1 to point 2, and then trying to evaluate the value of pressure and volume in these two different states, then he finds that the value of n is almost close to 1 for an isothermal process. See, I am saying that it's close to 1. Why? Because this achieving an isothermal state is almost impossible in the context of thermodynamics. Okay, it's very difficult to achieve an isothermal state. Okay, but even after say an idealized experiment, if he is able to achieve an almost close to isothermal process, then he finds that the value of n in those kind of experiments is turned out to be 1. Okay, similarly, if is able to achieve an adiabatic process, that is basically a type of process where there is no heat interaction. So in say in the piston cylinder example, if we say that the walls of the piston are insulated, okay, let me just draw the diagram. Say in the piston cylinder example, if we say that the uh, walls of the piston are insulated, okay, so there is no heat interaction in those kind of processes, okay. So such kind of processes where there is only change in the work and the energy interaction and the internal energy of the system, these kind of processes are known as adiabatic processes, okay. So say if we are going to write the first law of thermodynamics for this kind of process, okay, so we don't know whether it's cyclic or not, so just write the generalized law, it is delta q, sorry, q1 to 2 as E2 minus E1 plus W1 to 2, okay. So now if we are compressing this piston, we know that we are doing work on the system, so work done from 1 to 2 would be negative or positive. You can write on the chat box. We are compressing the piston. Yes, thank you. So this would be negative, okay. Then we are saying that if we are insulating the walls of this cylinder, okay, if we are insulating the walls of this cylinder, say again, if even if this piston surface also insulated, then the entire process is going under an adiabatic state, right? There is no heat interaction, so this would be equal to 0, right? So in that case, the net change in the internal energy of the system, E2 minus E1, would be equal to 1 to work done from 1 to 2, because this was negative, right? So if we take it on the right hand side, on the left hand side, then we will have E2 minus E1 is equal to work done from 1 to 2. So the net change in the internal energy of the system is primarily because of the work input in the system, okay. There is no contribution of heat in the change of the internal energy of the system, okay. So is the example for the adiabatic process understood? Yes, yes, exactly. Yes. So if it was not adiabatic, then the change in the uh, energy, the internal energy would also be contributed because of the work interaction. So we have to check both of them, okay. You can say that adiabatic case is a special case of a polytropic process, okay. It's a special case for the polytropic process, okay. You will again see that isothermal process also a special case for the polytropic process. Why? Now see, if we say that the process is isothermal, okay, and now if we say that for an ideal gas, you will eventually, when we go into the course, we will see that for an ideal gas, this energy interaction can be written as okay, for an ideal gas only, okay, not for any kind of gas, for an ideal gas, okay, Cv times T2 minus T1, okay. Now if I say an isothermal process, what would be the net change in the energy? What will be E2 minus E1? For isothermal process, temperature are constant, T1 is equal to T2. What would be E2 minus E1? 0, right? Yes. So it will basically mean that the net change in the internal energy is 0 for an isothermal process for an ideal gas, okay. So E1, sorry. Now in that case, we will have work done from 1 to 2 is equal to, heat interaction is equal to net work interaction, okay. This becomes a special case when we are considering isothermal process, okay. So you are clearly seeing now for an adiabatic case, this is the special case. So this is for the adiabatic case, and this is for the isothermal case, okay. I'm just giving examples, specialized examples, okay. It's not always true, okay, but special cases this is true. Now for a polytropic process where we do not know what happens to the net energy interaction or the net heat interaction. So these kind of processes will follow the first law of thermodynamics, the general first law of thermodynamics. Okay. So giving a particular special value to this index n simplifies our calculations, right? So that's what we mean by adiabatic or isothermal or a polytropic process. So in general, you can consider all processes to be polytropic. We do not know the value of index, okay? Value of the index n, okay? Once you specify that the process is isothermal, you know O. Now n will be equal to 1. So for an ideal gas, we will have the net heat interaction equal to net work interaction. Okay. Now again, if it is adiabatic, then we will have the net change in the internal energy is the net work input. Okay. So these are a special case for a polytropic process. Okay. So is that clear? Examples we will see. If you are going to want to know specific examples, so we will deal with this when we are dealing with cycles. Okay, special cycles such as the Carnot cycle, the Otto cycle, the diesel cycle. We will deal with Carnot cycle in this course, of course. So we will see that what the specification of an adiabatic process means in that cycle. Okay, what implication does it have on the cycle or the PdV plot or the TS plot? Okay, specifically in a TS plot, what does a adiabatic process mean? Okay, we will see that in that we'll understand it in a better way when we're dealing with cycles, but for now you can just consider it as a process where the net heat interaction is 0. So those processes are known as adiabatic process. Okay. Okay then. Oh, okay. Since the question is already revealed, so this was a question discussed by Professor Anand. I wanted to ask, but I already scrolled past it. So what is the cyclic integral of a property? So when we look into it, we find that since the properties are state functions or point functions, this depends only upon the value of the property and the depend on the value of the property at the particular state points. Okay. So if it is cyclic integral, it will basically mean that we are starting from an initial point. After doing entire process, we are coming back to the initial point. Okay. So in that case, since the initial and the final point are same, and the value of these properties depend only upon the state points in the PdV plot, in the PV plot, then we will have that V1 minus V1 equal to 0. Again, similar, T1 minus T1 equal to 0. So the cyclic integral of the property of the system is 0 in the case of thermodynamics. Okay. Then what can you say about the cyclic integral of work? Would that be 0? Work or heat, would that be 0? This is the next question. No. Okay. Can you give a one-line answer to it? Or you can unmute yourself as well. It's completely fine. Okay. So you see that as I've already mentioned, and also we also took an example where we saw that the work interaction depends on the path. So work is a path function. So it will depend on the path followed by, yeah, of course, exactly, thank you. So work interaction would depend on the path followed while achieving the process. Okay. So if we see in this example that if you are doing a cyclic integral in this along this line, so while going from say point 1 to point 3, we are going through a line 1 to 2, then 2 to 3. Okay, that's the first path. Okay, then while coming back, while completing the cycle, we come back from 3 to 4, then 4 to 1. Okay, then since the area under these two curves, that is from 1 to 3 and 3 4 1 are different, so it will have a network interaction. Okay, it will have a network interaction, that is the area enclosed within this cycle. Okay, which in turn gives us the network done. Okay, and since this is definitely non-zero, then the work done in a cyclic process is non-zero. Okay, if this part coincides, then it will be 0, but then again it won't form a cycle, right? So the cyclic integral in the case cyclic integral work done in thermodynamic cycle is non-zero. Okay, since it depends on the path followed by the to achieve the process. Okay. Okay. So these are some important points to consider while we are dealing with work interactions. So these were very thoroughly discussed or explained by Professor Anand, but just for the sake of understanding and for the ease of solving the problems that we're discussing today, I will just go on to the points one by one. Just that's what we'll do. Okay. So work is an energy interaction between the system and the surrounding. Okay. So the important thing to note is that for the work interaction to occur, there has to be a system and a surrounding. Okay. By which I mean is that we require a donor, a receiver, and an interaction. That is, we need, say, from these terminologies, we need a system, a surrounding, and a boundary. Okay. So for the work to be realized, these three things has to be there. Okay. A donor, a receiver, and a boundary for interaction. Okay. And then the net work done by the system and the surrounding. This is basically the net work done by the system on the surrounding, and the work done by the surrounding on the system would be equal to 0. Okay. We will see some examples which will prove that. Okay. So right now you can just take this for granted, but we'll prove this while we are solving some problems. And even Professor Anand also proved this by solving some numerical problems in his examples. So we'll go through them so that this can be considered even more. Okay. Now, in line with this expression, if we have many systems that are having work interactions with each other, then the work done for system 1, then work done for system 2, work done for system 3, to work done for system n, where you can consider the last system as a surrounding, say, this summation would be equal to 0. Okay. Then work done for all the interactive systems, and you can consider the surrounding as also one of the system because it is interacting in the system. Then the work done from all the systems would be equal to 0. Okay. The summation of all the work done, work of all the systems would be equal to 0. Okay. This is very important. Okay. We will see how this comes into picture. This expression comes into picture while we are trying to evaluate the net work done. Okay. For different components of the thermodynamic system. Again, this is also very important. Then for the work to be done, the process has to be carried out by the system. It must be resisted by the surrounding. Okay. So the work to be achieved, the work done by the system must be resisted by the surrounding. Okay. So we will see what it means. Okay. So again, this is very trivial, but still. So F is equal to ma. Okay. It's the second law of motion. Okay. And unity, SI unit is in Newton. Okay. But at equilibrium, we will have that summation of all the forces is equal to 0. Okay. But summation of all the forces equal to 0 does not mean that the velocity is 0. Why? Because since summation of all the forces would be ma, and a represents a is equal to dv by dt, then a constant velocity will also imply a equal to 0, right? So it does not mean that velocity is equal to 0. Okay. Similarly, summation of all the forces does not mean the net work interaction equal to 0. So this part I was a bit not clear myself also, but what Professor Anand meant to say is that it may happen that if summation all of forces is equal, summation all of forces equal to 0 may mean that work interaction equal to 0, but it is not always necessary. So there might be some instances where the system is trying to achieve an equilibrium of forces, but while trying to achieve those in equilibrium, the system might have some amount of work interactions. Okay. So this was the specification given by Professor Anand. So it's a specialized case where we can have work done equal to non-zero for summation of where the summation of all the forces is equal to 0. Okay. Okay. So this was a very good example taken by Professor Anand where he showed that Sir Isaac Newton was sitting below the. Let me just draw it and just forgive my drawing skills. So this was the tree and Sir Isaac Newton was sitting below, and the apple falls upon his head, and that's how he discovers gravity, right? That's a very popular story. But in current case, now we are interested in what's the work done by the apple while falling from a height of 1.5 meters, say, just before reaching Newton's head. Okay, in this case, the apple is not colliding with Sir Isaac Newton's head, but just before reaching Sir Isaac Newton's head. What is the work done by the apple? Given that the drag force due to air is almost equal to 0. Okay, so to verify the statement that I just said just before, that for the work to be realized, there must be a resistance from the surrounding. Okay, so in this case, since the apple is falling free from any air resistance, that's why the net work done by the apple would be equal to 0. Okay, just before reaching Sir Isaac Newton's head. Okay, after it reaches, then again it imparts its momentum, then there is again work interaction. But just before reaching or the moment where the apple is having a free fall and there is no air resistance, then the work done by the apple in the atmosphere having no drag or air resistance would be 0. Okay, so so again there Professor Anand describes some non-quasic processes by giving some examples. So the piercing of a membrane separating a vacuum. Okay, so this example also I will just briefly go past it because Professor Anand described it very clearly. But it simply means that if there is a chamber, where where the chamber is separated into two compartments, where this line denotes a thin membrane or a membrane that separates these two compartments, where one of the compartments has a gas of volume V1 and initial pressure of P, and if we are able to successfully pierce this membrane or remove this membrane, then what will happen is that since the other compartment has a say volume V2 and has a pressure equal to 0, that is vacuum, then what will happen is that since the pressure is low, by the process of diffusion, this pressure will the air molecules will try to go, or gas molecules try to go in this region, right? The having region of having 0 pressure or low pressure. Okay, so since this area was already in a state of vacuum, that the pressure was equal to 0, so the expansion of this gas from an initial volume of V1 to a final volume of V1 plus V2 does not receive any kind of resistance from this region, right? And thus it is just having a free expansion, okay, or unrestricted expansion. That's just term used in the second statement. So in this case also, since the expansion of this gas, like if we consider if we consider this as our initial system, okay, then the work done for the gas to expand from volume V1 to final volume of V1 plus V2 would be equal to 0, because it's not receiving any kind of resistance for its expansion. Okay, that's why the work done is 0. Similarly, in the case of unrestricted expansion, is just the special case of this, so simply like that. And similarly, in the case of free fall also, that example of the apple falling on Sir Isaac Newton's head, also is an example of free fall. So in that case also, since it's not achieving any kind of air resistance, or if we consider the air resistance very very less, then the net work done is also 0 in the case of a free fall. Okay, so right now I'll just request you to wait for a minute. I'll come back as soon as possible. I just go have to. Okay, thank you. Just wait for 1 minute. Okay, I'll just come back. You can go through the diagrams. It's a similar diagram used by Professor Anand in his lectures. You can go through it. I'll explain it once again, and you can ask any doubt if you have. Okay, just forgive me. I'll just take 1 minute. So I'm again sorry for the delay. So in this diagram, this diagram is was used to show the difference in work interaction in the case of an unresisted, a partially resisted, or a fully resisted process. Okay. So in this context, Professor Anand used the example of free fall and a partially resisted fall that where the air is relatively thick and offers some kind of resistance to the falling person. And the third example was the case where the air is very thick and the person also uses a parachute to resist his descent from the height, okay, from particular height. So if we consider a case where the mass of this person is say 60 kg, then the weight of this person will be almost be equal to 600 newton. Okay, just rounding it up to 600 newton. If we consider it to be 10, of course we are just saying that we are rounding up the weight of the person to 600 newton. Okay, just to simplify the calculations. So in the case of an unresisted fall or a free fall where the air is very very thin and the air does not provide any kind of resistance, so even if the air exists, the air resistance is almost equal to zero because air is very very thin, then the net work done by the person while falling from a height of say 1000 meters is equal to zero. Okay. In the case of a partially resisted fall where the weight of the person is again 600 newton and the air resistance provided by the atmosphere is say 50 newton, in that case the net work done would be only be equal to the resistance that the person feels times the uh, height through which he falls. Okay, so say similarly which is just work done would be equal to force times displacement, where again force, let me just write it. Okay, work done is force times displacement, or here force is mg and d is equal to h, then work done is mgh. Since this F, the resistance force is equal to only 50 Newton, right? Then the net work done in this partially resisted fall would be 50 into 1000 or 50,000 joules or 50 kilojoule. Okay. Now similarly, if we consider a third case where the fall is fully resisted because of the thick atmosphere and the use of a parachute, then the entire weight of the person is being balanced by the drag force, which is why people use parachute for safe landing. The weight of the person is balanced by the drag of the atmosphere that the parachute and the person also experiences. In that case, the net drag force is F, but it will be equal to 600 Newton. It balances the weight of the person. Then the net work done from 1 to 2 is 600 into 1000. That is the height through which the person falls. Then work done is 6 lakh joules or 600 kilojoules. Okay. So I hope the example was clear. Like, it's just trying to make you understand the effect of resistance on the work interaction, specifically in the PDV work. Okay. So I hope it was clear. So work done has to be resisted by some other kind of resisting force. Okay. So in this case, in the case of free fall, the free fall is resisted by the drag. Okay, the air drag. Okay. So I hope it is clear. Okay. So now we'll briefly introduce you to different kind of work interactions, primarily because in the context of thermodynamics of work interactions, we are mostly concerned with the PDV work, because we usually deal with systems that primarily have PDV work, because since in the mechanical context, if we are dealing with say petrol engines or diesel engines, the piston cylinder mechanism in the engines can be considered to have primarily have PDV work. Okay, the expansion of the gases within the combustion chamber can be considered to be achieved by the PDV work. Okay, and that's why the analysis of the thermodynamic system in the perspective of PDV work is very very important or interesting in the case of thermodynamics from the perspective of mechanical engineering. Okay, but then also there are different kind of works as well that I mentioned before, So there is gravitational work, the example that we just discussed, where the work is given by mg into h, or the gravitational potential energy. Okay. Then there is shaft work that usually happens in the case of a shaft rotating in a fluid, that where the work is transferred to the fluid by the rotation of the shaft. So the net work interaction is given by t into theta, where theta is the net angular displacement, that can also be written as into omega into t. So the final expression is given by 2 pi n into t times the time for which the rotation is being achieved. Okay. Then there is electrical work, where power is given by V into I, where V is the voltage or the potential difference, and I is the current through the load or the electrical equipment. Okay. Then the net work done will be given by IV into T, or power into time, because power is work done per unit time, then work is power into time, right? Then we will have work done is equal to IV into T, or I square R into T, where we use the Ohm's law, where V equal to IR, right? Then we can write W is equal to I square R into T. Okay, here T is time. Okay, time in seconds if you are dealing with SI unit. Okay. Then there's surface tension work, that is work done in the case of work done by the surface tension of the liquids, where if the surface area of the liquid changes, then there is a work done by the surface tension forces to overcome that change in the surface areas. So that is given by sigma into delta A. Sigma is the coefficient of surface tension, and delta A is the net change in the area, surface area. Okay. Then finally we have spring work, where work done from 1 to 2 is given by half into kx square. Okay. Now force is given by kx. Then the net work done would be, net spring force is given by kx, where x is the displacement of the spring. Then work done is integral of f into dx. If we do this integral, we will get w is equal to kx square by 2. Okay. So now let's go on to this example. Okay. So this example was discussed by Professor Anand, but let us just go through it once, so that I am going through it primarily because I want to emphasize that equation, that the sum of net work interactions in a number of systems is 0. Okay, so we realize it once we are able to solve this question. Okay, so let me just go through it once. A DC electrical motor is used to operate a hoist mechanism. A DC electrical motor is used to operate a hoist mechanism in a crane. The motor is supplied with 300 volt and 10 ampere from a DC source for a period of 2 minutes. Okay. We have V, I and T, then we can evaluate the net electrical work. Okay. The torque provided by the motor to hoist shaft is 250 Newton meter at 50 rpm. Then we have the net torque T and the angular velocity. Then we can evaluate the net work shaft work. Okay, 2 pi n T into the time T. Okay. The hoist mechanism lifts a mass of 2.5 tons through a height of 5 meter. Then since we have mass and height, we can find the net gravitational work, right? Calculate the work interaction for a DC source, the motor, the hoist and the mass. Okay. Again, it's a very simple problem. If you observe, like all the parameters are given, but it's as a introductory lesson, or introductory course to thermodynamics. I guess solving this problem will give us a very good insight to the field of thermodynamics. Okay, we'll see how different kind of work interactions are achieved, and how the equation, that is summation of all work interaction in the system, is 0. Okay, so we will see that. So first we can draw the diagram. Okay, so we draw a diagram for the electrical motor. Okay, so electrical DC source and the motor. Just 1 minute. Okay, it has a voltage of 300 volt and power in a current of 10 amperes, and it runs for 120 seconds or 2 minutes. Okay, then the power is supplied to a motor, where the motor rotates the shaft at a torque of 250 Newton meter and angular velocity of 50 rounds per minute. Okay, then this hoist mechanism is used to lift the weight to a height of 5 meters. Okay, So net work done by the electrical source would be Vi into T. Since the work is done by the electrical source, so the sign convention would be positive or negative. Work done positive, thank you. Since work is done by the electrical source, right, on the work is done by electrical source on the motor, so this work interaction is positive. So we will have work done as Vi into T, so 300 into 10 into 120, so we will get 360 kilojoules. Okay, now the work done by the motor. So see, in the case of motor, now we will have two kind of work interactions: the work input from the electrical source and the work output to the hoist mechanism, right? So since the work is done on the motor by the electrical source, the work interaction due to electrical source would be negative, right? And the work done by the shaft would be positive because the work is done by the motor on the hoist mechanism. So this work done, the shaft work would be positive. Okay. See, don't get confused with the sign convention. Okay, it is very important. That's why I'm going it through it very slowly. Okay. Then the electrical work done on the motor is 360 kilojoules. They do negative because the work is done on the motor. Okay. Then to find a shaft work, we need to evaluate this expression tau into theta, T into theta. There theta is omega T. Then if we evaluate this expression, we get that. You can see how we have evaluated this expression. Then once we evaluate the expression, we get that the net shaft work is around 157 kilojoule. Okay, positive. So the work done by the motor is equal to minus 203 kilojoule. The net work interaction in the motor is minus 203 kilojoules. Okay. You can basically say is that the work done upon the motor is greater than the work supplied by the motor on the shaft. Okay. It's also very, what to say, elegant way of introducing into the concept of electrical efficiencies, mechanical efficiencies, or the concept of efficiency in the case of thermodynamics. Okay. Since none of the equipments or processes are 100% efficient, none of the electrical equipments or mechanical equipments that we are able to create are not 100% efficient. That's why you can see that the network supplied by the electrical motor is lower than the network input from the DC source. Okay. Then this also a very good way to check whether your solution is correct or not. Okay. Okay. So the work done by the hoist mechanism. Okay. Again, what is 250 in calculation? Okay. So is it fine? Hoist work calculation. Okay. Oh, 2500 is the mass of the weight that it is lifting. 2500, 2.5 tons, right? To 2500 kg. Is that clear? Okay. Is it clear? In tau theta calculation above. Okay. It's 2 pi n into T. Okay. You can see now it's 2 pi n into T. Is it clear? Is it clear? What is T? T is the torque. Okay. The torque that is being supplied on the motor from the hoist mechanism from the motor. It is given in the question. Okay. T is, if I look there, okay, T is 250 Newton meter. Okay, you are right. T is 250 Newton meter. This is the torque T. Okay. Okay. Thank you. I hope it is clear for everyone. I thought that since this was already done by Professor Anand, I just skipped through it, but you can just check. Okay, it's fine. Okay, I will just explain it once. Okay, see the net work interaction by the shaft mechanism is given by T into theta. Okay, where theta can be given as T into omega into T. Okay, now omega can be written as 2 pi n into T, sorry, 2 pi n, omega can be written as 2 pi n, and torque is the capital T is the torque and small t is the time. Okay, now this value of this calculation is done here, which gives 2 pi n into T is equal to 1308.9 watt. Okay, and since we are running it for 120 seconds, so it is into 120, so this will give around 157 kilojoules. Okay, so I hope it is clear now. So now for the hoist mechanism again, since now it is it is receiving a work of t theta from the electrical motor, so it will have the net work input as minus t theta, so it will be minus 157 kilojoule plus mgh, that is the work done by it to raise the weight, so it will be equal to 2500 kg into 9.81 into 5, so we will get that it is minus 157 plus 122.6 kilojoules. So the net work interaction in the hoist mechanism would be equal to minus 34.4 kilojoule. Again, you can clearly see that the negative sign basically tells us that the network, there is a network input to the hoist mechanism. Okay. Similarly, the work done by the mass would be negative entirely. Why? Because the mass is initially stationary and it is being lifted up by the hoist mechanism. So work is done on the mass. So the net work on the mass will be minus 122.6 kilojoule. This is basically mg into h. Okay. Now the interesting thing is, since we have these four systems interacting with each other, and if we sum up all these work interactions from these different systems, we'll get that the network interaction is equal to 0. If we sum up all these work interactions, this first one was 360 kilojoule, second one was 203. Now for the hoist mechanism it was minus 34.4. Oh, I mean again sorry, this is minus 34.4. And then minus 120.6. If you sum up all these work interactions, you will find that the sum of all the work interactions for the systems would be equal to 0. Okay. Okay. So this example again I will have to discuss. It was discussed again by Professor Anand, but this example also has a concept of PDB works, so I would like to discuss it. Then we will directly go to the problems that I have set up for this week's session. Okay. So this problem states that tank A and the piston cylinder arrangement B are connected through pipes as shown. Okay, the diagram is given here. I will just go through the diagram once I go to the question. Okay, the piston is frictionless. Now tank A contains nitrogen at 300 kilopascal and its volume is 0.4 meter cube. Okay, it requires 150 kilopascal to leave the piston. Okay, so it requires at least a pressure of 150 kilopascal to leave the piston. Okay, as the connecting valve is opened, nitrogen flows into the piston cylinder arrangement B, and as we open this valve, nitrogen through the tank A flows through these pipes and enters the piston cylinder arrangement at B. Let me just denote it, A and B. Okay, and attains a steady state after some time. Sorry. And attains a steady state after some time. Then what is the final pressure and the work interaction in nitrogen if the initial and final states are related by the expression PV equal to constant? Okay. So what the question is basically trying to imply is that uh, okay, just 1 minute. Yes. So initially we have a system, we have a chamber where it contains the nitrogen gas, okay, which has an initial pressure of 300 kilopascal and volume of 0.4 meter cube. Now, and initially this piston was at the bottom of the piston cylinder mechanism, okay. So it is said that to lift this piston we need at least a pressure of 150 kilopascal, okay. So what happens is that once you open this valve, the since the pressure is is almost zero, is zero here, then the nitrogen gas flows through these pipes and enters this piston cylinder mechanism. And once the pressure here is 150 kilopascal, piston uh, the piston starts to move up and then encloses a certain volume after the system achieves an steady state, okay. So so we are asked to find out what is the final pressure in this system and the work interaction for the nitrogen gas, okay. So is the question clear? Okay. So just 1 minute. I just hope I'm not missing up any. Okay, it's fine. Okay. So since it is mentioned that the work interaction is given by the relation PV equal to constant, so we can find the final volume V2 uh, from this relation, right? So P1 will be equal to P2 V2. So V2 would be given at P1 V1 divided at P2. So see why P2 is taken as 150. Okay. So what happens is that initially the pressure was at 300 kilopascal. Okay. So once the valve is opened, uh, the nitrogen from the chamber A goes to the piston cylinder mechanism at B. Okay. So what will happen is that since the number of air molecules or nitrogen molecules in the chamber reduces, the pressure in the chamber will also reduce, and the pressure in this chamber will increase up to 150 kilopascal, because it is after 150 kilopascal only that the piston will start to move, okay. So even if it is 149, the piston won't move, so it won't have any volume within the piston cylinder mechanism, okay. So once the pressure reaches 150 kilopascal, like once enough molecules of nitrogen has passed through the pipes and reached in the this piston cylinder mechanism, then once the pressure reaches 150 kilopascal, the piston will try to move up, and while moving up, the pressure, since the piston moves up very slowly, the pressure within this region remains ideally constant. So pressure remains equal to pressure remains constant, that is equal to 150 kilopascal, okay. And after it moves up to a certain height, it achieves a steady state, okay. So the final pressure then becomes 150 kilopascal for the entire system, okay. So the system in this case, see, this important loop. So the system in this case is both this chamber and this area, okay. Is it clear? In this case we are just ignoring the volume of gas within the pipes, okay. It was discussed by Professor Anand that he is ignoring the volume of gas within the pipe and the valve, okay, considering that the diameter of the pipes are much smaller than the size of the chambers, okay. So once we do that, once we apply the PV equal to constant relation, we find that V2 is equal to 300 into 0.4 divided by 150, so it gives us V2 is equal to 0.8 meter cube, okay, where 0.8 meter cube is the volume of the entire system, okay, the volume of this plus this, okay. Because see, logically it's extremely impossible, right, that if you're considering the volume of V2 is only the volume of this region, then it basically implies that V2 becomes 0.8, double the initial volume in the closed chamber. So that's not possible. So we're considering the system to be both the initial chamber where the nitrogen was stored and the volume enclosed by the piston once it moves up to a certain height, okay. So the final volume is now 0.8 meter cube, twice the volume of the initial nitrogen in the enclosed chamber, okay. So the work done from 1 to 2 can be again be given by the integral of PdV from 1 to 2, where since I told that while the piston is expanding, so the where the volume within the piston is expanding, the pressure is remaining constant, right? So in that case, the pressure P would be equal to constant. So pressure will come, the P will come out of the integral. So the work done will be given by P into V2 minus V1. Okay, is this clear? Yes. Then once we substitute the value of the pressure P, the steady state pressure is 150 kilopascal. So we substitute the value of pressure of 150 kilopascal here and substitute V2 and V1. So we get that work done by nitrogen gas is 150 into 0.8 minus 0.4. So work done by nitrogen gas is 60 kilojoule. Okay, and this will be positive. Why? Because since the gas is expanding, the since the piston is moving up against the atmospheric pressure, so the work is done by the system on the atmosphere. Okay, so that is equal to 60 kilojoule. Now what is the work done by the atmosphere in this mechanism? So work done by the atmosphere would be minus PA times V2 minus V1, because the piston is moving up, so the work is being done against the atmosphere itself. So work done will be minus P atmosphere minus the change in volume. So it will be given by minus PA into V2 minus V1. So work done by the atmosphere is minus 40 kilojoule, or it basically implies that work is done on the atmosphere. Okay. Now you can now you may ask that, then now if we consider the work done by the piston cylinder mechanism, work done by nitrogen gas and the ATM and the atmosphere is two different systems, then why the summation of the work done by nitrogen and the atmosphere is not equal to 0? If we sum it up, we get that 60 minus 40 is 20 kilojoule. So what is the remaining, where does this additional work interaction comes from? Can anyone please tell? See, you are summing up the work done by the nitrogen gas and the atmosphere, and it's not coming up to be 0. We saw that work done by the system and the surrounding is 0. Then why is this additional work coming into picture? Are we? Yes. Not exactly frictional work, because it is saying that the piston is frictionless, but you are in the right direction. It's basically the work done on lifting the piston to achieve that enclosed volume within the piston cylinder mechanism, right? So there is an gravitational work done, right? So now we see that, now if we solve this equation, that is work done by nitrogen gas, work done by atmosphere plus the work done by the piston, we get that there is a work done by the piston. So it will be given by minus 20 kilojoule. Now this minus 20 kilojoule implies that the work is done on the system to lift it to a height of h. And if we would have been given the value of, say, the diameter of the piston cylinder mechanism and the mass of the piston, then we could have easily found out what is the height through which the piston has been lifted. Or even if we got the mass of the piston, from this we can find the height. And since we already know the volume enclosed is 0.4 meter cube, then we can find the h. Okay, find h, because the final volume is 0.8 meter cube and the initial volume was 0.4 meter cube. So the volume enclosed would be just 0.8 minus 0.4, which is 0.4 meter cube, right? If we get the mass of the piston, then we can find the height of the piston as well. Okay, from this equation. Okay, so now let us go to the questions. Okay, let me just. Okay, so is the screen visible? The questions visible? Okay, so let us go to the first question. It's very simple again. A load is connected to a 12-volt battery and the load draws a current of 20 amperes an hour. What is the work interaction for the battery in kilojoules? very simple question. Actually, just use the, so here you are given V, you are given V, you are given I, and also given T. So in kilojoules, okay. So I've got one answer. So others, is it the same? Work interaction for the battery. No, V is equal to I into R, right? Yes, no, just tell me the numerical value. Do the calculation and tell me the answer. I have also not evaluated it. Just want formula is correct. Just substitute the values and find the answer. A64 kilojoule. Okay, that's correct. It's A64 kilojoule. And the second question, what is the resistance of the load? Simple, just use the Ohm's law. V equal to IR, R equal to V by I. V is, yes, exactly, it is 0.6 ohms. 0.6 ohm, okay. Now look at the second question. Simple, very conceptual question. If the value of n is infinitely large in a polytropic process, PV, sorry, it's PV to the power n, okay. PV to the power n, just correct it, okay. PV to the power n equal to, okay. Then the process is, yes, you can write the answers. DC isochoric, yeah, okay. So the answer is it will be isochoric. Why? Again, see, if n is infinitely large, then the value of P becomes insignificant in this equation, okay. So it will basically imply that V is ideally equal to constant. Yes, exactly. So V equal to constant would mean an isochoric process, okay. So usually students get intermingled with isochoric and isobaric. So a simple way to understand is isobaric, okay. You know that bar is the unit of pressure, in one of the units of measuring pressure, right? So since it's isobaric, you can consider it, since it is related to pressure, then isobaric would imply a constant pressure process. And the other one, you can consider it to be the constant volume process, okay. Just to distinguish it, I'm just saying my way of understanding it. Again, there can be various ways to understand it, but it's fine, okay. So now the third question, okay. So this week's question, okay. So this week's question are like not MCQ type or anything. So it's primarily some numerical questions. So you need to solve it thoroughly by yourself. So what I will do is, since we have limited time, I will give a certain time limit to every question. Okay, it's completely fine. Now you can go through question number 3. You can go through a question. I will give you a say time limit of say 5 minutes. You can try to solve it and then tell me what's the answer. Okay. Let me just go to the question. I hope I can simplify it. Air undergoes two processes. Process 1 to 2, expansion from P1 300 kilopascal to V1 0.019 meter cube per kg to P2 150 kilopascal, during which the PV relation is given by PV equal to constant. Process 2 to 3 is a constant pressure compression, V3 is equal to V1. Process to V3 equal to V1. Okay. Determine the work done per unit mass. Okay. So let me just draw the PV diagram for this case. So what it tries to mention is that, so this is the first process 1 to 2 is an expansion, okay, and 2 to 3 is a compression. 5 minutes, so 7:35 I will ask the answer. I will show the solution. Before that you can give the answer. It's fine. So this is 1, 2, 3. Okay, it's a process, not a cycle. Okay, so we are ending up in different state points. Fine. So what it tells is that V1 equal to V3. P1 is equal to 300 kilopascal. V1 is 0.019 meter cube per kg. See, it is in meter cube per kg, so it is specific volume. Okay. Per kg. And P2 is 150 kilopascal. And we are given that P1 V1 equal to P2 V2. So we need to find the net work interaction in this cycle. Okay. And V1 equal to V3. And this process 2 to 3 is constant pressure process. Okay. So we need to find the net work interaction. Here P equal to C, here PV equal to C. You take your time. Very simple. First find the value of V2, then find the net work interaction. So what does PV equal to C imply, or what is the PV work in the case of PV equal to C? Find that work interaction. Then the second work done is very simple. 2 to 3 is constant pressure process. It will basically P into delta V. Find that and tell me the net work interaction. Are there any solutions? Not yet. Take your time. You have 2 more minutes. Try to find the work interaction in the case of a PV equal to C process. PV into constant is equal to constant process. So find out how the expression of work interaction is in the case of that, and find the network interaction and check the units. Okay, it's also important. This specific volume, then pressure is in kilopascal. So okay, 1 more minute, then I will try to show you the solution. And then 11 kilojoule. Okay, we have our first answer. 11. I would suggest that you check the units, specifically the decimal points. Okay, I'll wait for 1 more minute. Let's see if others also say the answer. Okay. just check the calculation, my calculation as well. So 36.7. The network interaction. Process 1 and 2 both. Check the minus sign, plus signs, and then tell me the answer. Okay. So, okay, actually 11 was close. It was just missing by decimal point. So, it's actually 1.1. So, let me show you the solution, okay? So, if I go, yes. So, this is the question. So, we have PV equal to constant. So, the work done will be given by this expression, right? P1 V1 into ln V2 by V1. Okay, PV is equal to constant. It basically implies an isothermal expansion. Okay. Then for isothermal process, we know that P1 V1 is equal to P2 V2. Now, since we do not know V2, we use this expression to find the value of V2. Okay. Once we do it, we find that V2 is equal to 0.038 kg per meter cube. Okay. Then work done from 1 to 2 is will be given by this expression. Substitute the value of P1 V1 and ln V2 by V1. Then we will get that P1 is 300 kilopascal, V1 is 0.019 meter cube per kg. Then we find the natural log of V2 is 0.038 meter cube per kg and V1 is 0.019 meter cube per kg. So once we do the calculation, we get that the work done from 1 to 2 is 3.95 kilojoule per kg. See the units, kilojoule per kg, because it was specific volume, it is meter cube per kg. So we have work done in kilojoule per kg. Is the units clear or the calculation clear? Okay, I hope it's clear. Yeah, thank you. Similarly, now for the process 2 to 3, it said it is a constant pressure compression. Okay, so even if you, by the very logic, you will understand that compression means there is a force that is compressing the air against the system. So work is done on the system. But then also, if you are confused with the convention, sign convention, just go on and substitute the volumes correctly. Okay, so pressure is constant, so it is 150 kilopascal. So work done from 2 to 3 would basically imply work done P times the final volume minus the initial volume. Okay, so the final state is 3 and the initial state is 2. So we substitute V3 minus V2. So V3 is 0.019 meter cube per kg and V2 is 0.038 meter cube per kg. Once you substitute it, we get that the work done from 2 to 3 is minus 2.85 kilojoule per kg. So minus sign itself implies that the work is being done on the system. Okay. So to find a net work, just sum up these two work done, then work done from 1 to 2 and work done from 2 to 3. Once you evaluate it, we get that W net is equal to 1.1 kilojoule per kg. Is it clear? Just missed by a decimal point. It's correct. The method should be understood. Final solution is important, but the method is more crucial. So, and I guess Professor Anand also emphasized upon to check the units again and again. Okay, so it's very important. Is it clear? Yes, no. It's a very simple problem, but okay, thank you. But it's important to know as an introduction to thermodynamics and the various problems that we are dealing with, that we will eventually deal with. Okay. So the next question is again a bit more lengthy, so we can go through it once. Okay. A piston and cylinder machine containing a fluid system has a steering device in the cylinder as shown in the figure given below. Okay. This is the steering mechanism. Okay. The piston is frictionless and it's held down against the fluid due to the atmospheric pressure. Okay. So pressure is atmospheric outside of the piston. The steering device is turned 10,000 revolutions with an average torque against, sorry for the spelling, against the fluid of 1.275 Newton per meter. So they have mentioned the torque here. Okay. Meanwhile, the piston of 0.6 meter diameter moves out to 0.8 meter. Okay. So piston moves a distance of 0.8 meter. Find the net work transfer for the system. Okay. So again, it's a very simple question, but the question is lengthy. Okay. So you can go through the question once. I will give you again 5 more minutes. So 7:46, I will ask you for the answer. So let me explain you the question. Okay. Meanwhile, you can, since you have the question is visible on the screen, you can take the numerical values and try to start solving it. But just for those who are not able, who would find it a bit difficult to understand the question, I will try to make you understand. See, it is a very interesting what to say, observation done by our late Professor S.K. Som. In his lectures, he used to mention that thermodynamics is a very interesting subject. Why? Because the questions that that are created are usually very long. Okay. See, the question 4 is also very long, but once you see the solution, you will find that it is only a 2 or 3 line solution. See, that's why. So thermodynamics in its very essence is a highly conceptual subject. Okay. Unlike fluid mechanics, like where there are lots of concepts also important, but there are lots and lots of derivations. Compared to that, thermodynamics is a very highly conceptual subject. So once you know the concept, the solution is very easy to find. So similar to this, here the question is very lengthy, but once you know where to substitute the numerical values, it's actually very simple. Okay. So here there are two kind of work interactions. The first work interaction is by this steering mechanism on the gas within this piston cylinder mechanism. So it is steering for 1000 revolutions with a torque of 1.275 Newton meter. Okay, so you can find the net shaft work input work would be given by work shaft would be given by 2 pi nt. Right, here we do not need time because we are already given the total number of revolutions. So you can find the net work done from this expression. Then it is said that the fluid moves out the piston moves out up to a distance of 0.8 meter. Okay, so there is again a PD work involved in it, right? So the net work would again be given by force into displacement. So it is P into A into L. Okay, just substitute the value of this values in these expressions, then apply the appropriate sign convention, and then tell me the answer. Okay. So the piston is held down against the fluid. Okay, held down against the fluid. So pressure within the chamber is 101.325 kilopascal. Okay. So it basically trying to imply is that pressure is balanced inside and outside the piston. So because of this work interaction, because of the work supplied by this shaft, by this steering mechanism, there is an expansion of the piston, which results in the piston to move out to a distance of 0.8 meter. Okay, so we are asked to find the net work interaction. 7:46. Okay, 2 more minutes, then look at the solution. And very simple, just 2 calculations, this one and this one. Put the appropriate sign convention, then tell me the answer. So the question by its very essence may look very long and confusing, but it's actually very simple. That's the beauty of thermodynamics. Questions are complicated, answers are simple. Of course, once you know the concept. Oh, yes, that's correct, but I need the net work interaction. Work is done by the shaft as well, right? To give me the total work interaction in the system. See, if you see the system boundary, see the system is not considering the shaft within. Okay, so basically shaft is an external what to say, external interaction upon the system where the shaft is supplying work in this system, where the system is given by this red dotted line. Okay, so there is a shaft work within the system, you need to find that. And then because of this shaft work, the system is expanding and the piston moves out to a distance of no, it's not correct, just check the units and the calculations. Okay, and the system moves out to a distance of 0.8 meter. So by doing so, the system is receiving a work, shaft work of this amount and doing a work of this amount. Then tell me the net work interaction. So okay, so it seems that we are out of time, but it's very good that all of you were trying on your own side, from your own side as well. I'm really grateful for that. So let's see the solution. Okay, it's uh, t- uh, oh no, let me go to the solution. Okay, thank you so much for trying, but still just let's just try to look into the solution. Okay, so see, since the work is done by the shaft on the system, where the system is given by this red dotted line, then the net work done by the shaft is given by 2 pi n into t. Here the catch was that since in the question it specifically mentions that the shaft is rotating for 10,000 revolutions. There is no RPM given, no time given. They directly gave you a number of rotations for the entirety of the time. Okay. Yes, plus or minus. Give me the sign. That's important. uh, it's wrong. It should be negative. Think upon it while I'm discussing the solution. Since the work is done by the shaft, yes, thank you. It's good that you understood. See, since the work is done by the shaft on the system, so the work done by the shaft would be negative with respect to the system that is given by this red dotted line, right? So 2 pi n into t, it would be 2 pi into 10,000 into 1.275 Newton meter. Okay, all are in SI units. And so once you do the calculation, you get that work done by the shaft on the system is 80 kilojoule, or specifically I should write, sorry, minus 80 kilojoule. Okay, since work is done on the system, then work done by the system on the surrounding would be because of the expansion of this piston cylinder mechanism. So it is PA, pressure into the area of the piston into the length by which it moves out. Okay, so pressure was 101.325 kilopascal. That area is pi by 4 into 0.6 meter square into 0.8, right? The distance by which the piston moves out. So once you evaluate it, you get that W2 is equal to 22.9 kilojoule, and it's positive because the work is done by the system on the outer surrounding, right? So net work done by the system, the question it gives by the system, would be the net work input because of the shaft and the work done output because of the displacement work. So work input was minus 80 kilojoule and the work output was 22.9. So we get that W net is equal to minus 57.1 kilojoules. Okay. So it seems that we are running out of time. So let me give you one interesting question. Okay. Try to solve that, and we will see if you have enough time. Otherwise, we will stop it up to that only. But and I'll give you the solution as well as the question paper, so you can correlate the solution. But this one is an interesting question. Okay, just go through it once. I'll give you around 8 minutes for that, and then you can try to solve the solution. Try to solve the question. Okay. Question number 8. Okay. A cooling water nozzle disperses water into a stream of droplets. Okay. A cooling tower nozzle disperses water into stream of droplets. So basically, what happens is that I'll show you the diagram after the entire question is read. If the average diameter of the droplets is 60 microns, estimate the work required for atomizing 1 kg of water isothermally at ambient conditions. Okay. Given that, sorry for this again, surface tension of water in contact with air is 0.07 Newton per meter. Density of water is 1000 kg per meter cube, and water is assumed to enter a nozzle through pipe of 15 millimeter diameter. Okay. So the question is that there is a pipe. Sorry. having a diameter of 15 millimeter, 15 millimeter, okay, and and this and water flows out of it in the form of droplets, okay. Basically water is being atomized, okay. So, sorry. So there are again some holes, sorry, some holes at the exit that tends to atomize the water. So water will come out sprinkling out of this cooling tower, okay. Sorry. Okay, so initially water is flowing in the pipe, okay, and at the exit it is being atomized, okay. It is being formed into number of droplets where the diameter of each droplet is 60 microns, okay. So say if I zoom it, take your time, okay, for this question. We'll solve this question, and if you have time we'll solve other questions as well. This is interesting one, that's what I'm saying. So if we zoom it in each droplet, so the diameter of each droplet is 60 microns, okay. 60 microns means 60 micrometer, okay. And diameter of the pipe is, okay. So you are asked to find what is the work required to atomize 1 kg of water, okay. 1 kg of water. So see, the hint is in this term, surface tension, okay. So as I mentioned, the surface tension work is given by the surface tension coefficient sigma multiplied by the final area minus the initial area. So the initial area would be the area of the water, or the cylinder of water, because the say the pipe is in cylindrical shape. The area of the cylinder of 1 kg of water, okay. Are you able to understand it? Please, this is an interesting question, so if you have any doubt in my explanation, you can stop me and ask, okay. So 1 kg of water would imply a cylinder within the pipe, okay, cylinder within the pipe whose weight is 1 kg. Is it clear? It's important, just tell me yes or no. Is it clear? Yes, right. So this cylinder of 1 kg of water would have a particular surface area which is given by 2 pi, we consider natural surface area only, so it's given by 2 pi RL or pi dl, right. Now it is said that this cylinder of water is changed into n number of droplets, okay, where droplets are of spherical shape. So the surface area of each droplet would be given by 4 pi r square or pi d square, right. Is it understood? N into h, yes, I'm getting where you're going. Yeah, it's pi, yeah. So the trick is, first of all you need to find the number of droplets, because initial area, you know, right, this is the initial area, so this would be ai, okay. For the final area of the water, you need to find the area of the droplets, okay. Sorry, the number of sorry, number of droplets, okay. So what remains constant is the mass of water, right? Since the 1 kg of water is what to say, dispersed into n number of droplets, so the mass of water remains constant. So what we can do is that, say n into pi d square, n number of droplets whose surface, oh sorry, not pi d square, we are now dealing with volume, so n into volume of a single droplet into the density of water, because it is water droplet, would be equal to 1 kg. Is it clear? Now we know that the volume of, the volume of a spherical shape sphere is given by, in the terms of diameter, will be given by d cube by 6 into rho w is equal to 1 kg. Now d would be equal to 60 into 10 to the minus 6 meters, then n you can find by 6 divided by pi d cube into rho w. Evaluate this expression and give me the number of droplets that you get. This is interesting because, see, after you atomize 1 kg of water into, say, n number of droplets, the surface area of the water increases tremendously, like becomes very high compared to its initial surface area. And this change in the surface area results in work done because of the surface tension forces of the water. And that is what we are asked to evaluate. Okay. So we need to find the number of droplets in this case. Can you find it? Simple calculation. Okay. So for the sake of saving time, I'm really sorry that I'm rushing a bit because we are going past our time limit. So for the sake of saving time, let me just tell you the value. So once you do this calculation, substitute the value of d, you'll get that number of droplets is 8.842 into 10 to the power 9. Okay. Now you need to find the surface area of n number of this 8.842 into 10 to the power 9 droplets. Okay, so the area would be, say the final area would be 8.842 into 10 to the power 9 into pi d square, right? Pi into 60 into 10 to the power minus 6 square. That's the area. The total area would come around 100 meters square. Okay. Now you need to for this cylindrical shape you only know diameter, so to find the volume you need the length as well, right? So to find the surface area you need the length as well, right? So we know that volume of this cylindrical shape will be given by pi d square by 4. Let me write capital D so you are not confused. Pi d square by 4 into L into rho would give you 1 kg, right? Because we are dealing with 1 kg of water. If you have any doubt, you can just stop me at any point and ask that out. Okay, it's clear, right? Now to find L, you can just substitute 4. 4 will go up, so 4 divided by pi capital D square by rho. Right? You get the value of L, the length of the cylindrical shape of water within the pipe. Right? Now to find the initial surface area, it will be just be pi d, capital D into L. Then just substitute the value of L here. So L would be 4 divided by pi capital D square into rho, right? So it will can pi would cancel out, d would cancel out, so we'll be left with 4 divided by d into rho. So it will be 4 divided by 1000 into 15 into 10 to the power minus 3. Right, so this will go out, so we will be left with 0.267 meters square. Right, this is the initial area. Just see the difference in the area because of atomization. So once you know the value of this initial and the final area, just substitute it in this expression that work done from 1 to 2 is sigma into delta A, or 0.07 into 100 minus 0.267. So you will get the net work done as 6.98 joules. So is it clear? Thank you for the additional significant figure on the solution. And so is it clear? Okay, thank you. Then I'm sorry, I had 2 more questions planned, but I couldn't solve it given that time frame, and I too have an important meeting to attend. So I'm really sorry for my personal bias that I'm having today, but I'll upload the question paper as well as the solution sheet in the website, so you can just go to the course website and check the solutions. Okay, thank you again. Thank you for attending today's session. Let's meet. Thank you. Let's meet next week. Okay.